It's my pleasure to introduce Rasul Shafikov, who's visiting us for the year, and he's going to speak about polynomially convex embedding with real manifolds.
Thank you very much. I'm really happy to be able to give a Colloquium talk here. I was a postdoc in Stony Brook from 2001 to 2003, of which I have very fond memories. And in particular, during that time, I gave my first Colloquium talk. So what I would like to talk today is a specific problem in complex analysis, several complex variables. It is in a spirit which is a common theme in geometry when you want to embed manifolds into Euclidean spaces with specific property. So it all started with classical theorem of Whitney that any smooth manifold can be embedded into Rn for a specific n, and you preserve sort of the smooth structure, or there is a famous theorem of Nash when you preserve the Riemannian structure, or you can have an embedding of a complex manifold into a complex Euclidean space, in which case that gives you a special class of complex manifolds called Stein manifolds. And these, this problem is actually used to give a real analytic embedding of real manifolds into Euclidean spaces, the real analytic version of Whitney embedding theorem. And also, for example, there is a problem of Lagrangian embeddings of manifolds into R2n with a standard symplectic form. And this problem is somewhat reminiscent of this question of Lagrangian embeddings. The property that I would like to preserve through the embedding, or rather to have through the embedding, is called polynomial convexity. So my plan is to introduce polynomial convexity, give general properties, and then formulate the problem, maybe convince you that it might be an interesting problem to look at, and then I'll give some results, known results in this direction. So let's start with a definition of polynomial convexity. So we start with a compact set in Cn, and we define the polynomially convex hull of it, which is the following set. These are all points of z in Cn, such that p of z in absolute value less than or equal than the norm of p on a compact K, and we want this to hold for every p which is a holomorphic polynomial.
Is that the sup norm, or?
It's a sup norm on a compact. Yeah, so the reason why I wrote it this way is that this is a general way to define convexity with respect to a family of functions. So here I chose polynomial convexity, so that gives me polynomially convex hull. But in general, you can have, for example, you can take real linear functions, in which case you're going to have the geometric convexity, or you can define you can take rational functions, then you're going to get rational convexity, or you can take entire functions, in which case you're going to have the same notion as polynomial convexity, or you can have maybe plurisubharmonic functions, and then you have, there is a choice of functions that you can use here in the definition. And we say that K is polynomially convex. By definition, this means that K is equal to K hat. And it's sort of straightforward to see that for compact set K, K hat is compact. And if you take the polynomially convex hull of a K hat, you're going to have K hat again. So let's look at some examples and properties of polynomial convexity. So let's start with dimension 1. So in this case, there is a very simple description of polynomially convex compact. K is polynomially convex if and only if the complement of K in C is connected. So if you have a hole in your compact, then this hole will be in a polynomially convex hull of K. So it's really sort of elementary property. But in higher dimensions, there is no topological description of polynomially convex compacts, and things become more interesting. But we can take convex sets, and these are polynomially convex. So balls, polydisks are polynomially convex compacts. Another example, if I take a compact set in Rn sitting in Cn. So this Rn is spanned by the real part of complex coordinates here. So this will be a totally real Rn. Then K is polynomially convex. So any compact set of Rn is polynomially convex. But there is a result by ISO that says that, well, you take any compact K that has uncountably many points, then you can diffeomorphically map it into some Cn so that the image will not be polynomially convex. But here it is polynomially convex. And then my third example, if I take a holomorphic disk, so it's a continuous map from the unit disk in C into Cn, continuous and holomorphic in the interior, and attached to K. So I'm going to say that the boundary of the disk is contained in K. So, yes.
Two disks, it's a disk in C.
Oh, this is in C, yes. Then this is what we would say. And let's say F is not constant. Then the disk is in the polynomially convex hull. And that's immediate from the maximum principle. If you take a polynomial, compose it with this map, then you have a map in the disk. And if it takes certain values on the boundary, then in the interior it cannot take any bigger values. So that clearly indicates that this is this whole disk has to be in a hull. So the picture is like this. So this is K, and then, yeah, I'm sorry, unlike previous Colloquium speaker, I don't have any pretty pictures to show. But this looks sort of like this. So this will be in the hull. And in early development of the theory of polynomial convexity, people were wondering whether it's always the case that a non-trivial polynomially convex hull contains a holomorphic disk. And this was known as analytic structure in the hull. But Stoltenberg in the 50s already, or 60s, already found an example of a compact set in Cn who has a non-trivial polynomially convex hull, but it doesn't contain any analytic structure. So there is no map from, non-constant map from a disk inside the the hull. And the other thing that I wanted to mention, so here I was mentioning that any compact subset of Rn is polynomially convex, and one may wonder if this Rn is sort of a totally real submanifold. I will discuss it in detail later, but if you replace Rn by some other totally real manifold, then this will no longer be true. So there are these totally real disks, so they don't have any complex tangents anywhere, but still it's not going to be polynomially convex. All right, any questions?
Sorry, is the last thing you said that there are totally real submanifolds that aren't polynomial?
Yeah, you can have a totally real disk, which is not polynomially convex. So I want to give you two maybe reasons why polynomial convexity might be an interesting property to study. One is a fundamental result by Oka and Weil, which says that if K is a polynomially convex compact, then any holomorphic function in a neighborhood of K can be approximated by holomorphic polynomials. The way I'm going to write it is to say that the closure of holomorphic functions on K, and holomorphic function means holomorphic in some neighborhood of K. The neighborhood depends on the function, and the closure is in the sup norm on K, is equal to the closure of polynomials with the same norm. So polynomials are dense in the space of holomorphic functions. The converse to this is not true in general, but partial converse is the following, that if I take the space of continuous functions on K, and if polynomials are dense here, then you can say that K is polynomially convex. And this is a strong assumption. This implies, for example, that K cannot have any interior, because in the interior, these functions are going to be holomorphic, but continuous functions need not be holomorphic. So that's only a partial converse to Oka-Weil.
And also say Runge's name.
Yeah, so in one variable, this is exactly Runge's theorem. And well, in Runge's theorem, the way we teach it in one variable is we simply say that the complement is connected for this to hold. But that's exactly the condition of polynomial convexity in one variable. Yes?
So you said there were no topological characterizations in higher dimensions. But in the plane, saying the complement is connected to a special case like a Cantor set or a Jordan arc, which have connected complement, I was wondering if there were sufficient conditions like being a Cantor set or being a Jordan arc or being a Cantor set of small dimension that might apply.
Well, if you have a Jordan curve, then the complement will not be connected, right?
Excuse me?
If you have a Jordan curve in C, then the complement is not connected.
Jordan arc.
Oh, arc. So a Jordan arc will be, if it doesn't have self-intersections, it will be polynomially convex. So this, so this is if and only if.
In the plane, yes.
No,
but
not in higher dimensions.
No.
This is in one variable, yes.
Yes, I know the one variable case very well, but I don't know the higher dimensional case. I just was wondering if there were any topological sufficient conditions. I know there's no characterization, but you can't say like every Cantor set is polynomially convex or every Jordan curve is polynomially convex in higher dimensions.
In high dimension, no.
Nothing like
No. Yeah, so see, this is the thing, that K is here. What I said is that any compact set in Rn is polynomially convex. And if it has uncountably many points, like Cantor set or something like that, then you can embed it in some Cn so that it's not polynomially convex. So the properties of K do not determine whether it's going to be convex, polynomially convex or not.
rectifiable arc or something.
In Cn, yeah. So then it's there is a characterization. Yes, I'll mention that in a second.
Just take a homomorphic.
Well, and the other reason why maybe polynomial convexity is interesting is that there are relatively simple questions to which we do not know the answer. For example, a closed ball, is a convex set, so it is polynomially convex. Then you can take the union of two balls, and it's an exercise to disjoint union to show that it's polynomially convex. And then it's a theorem of Kalin that a disjoint union of three balls is polynomially convex. But we have no idea whether the union of four balls is polynomially convex or not. This is an open problem for 60 years now, and we haven't got any close, I think, to the answer.
The union of bidiscs.
The union, there are counterexamples to the union of four, or even ellipsoids. You can construct four ellipsoids that are not polynomially convex, but not the balls. All right, and now I'd like to formulate the question that I'm interested in, and I'm going to call it the embedding problem for the purpose of this talk. I'm going to call M the space of all closed, smooth manifolds of dimension M. And the question is to find the smallest capital N, which will depend on M, such that for any manifold in this class, there exists an embedding, smooth embedding of M into Cn, such that phi of M is polynomially convex. Okay. So let me sort of make a few trivial observations about this question. First is that, well, if I take a manifold of dimension M, then by the Whitney embedding theorem, I can embed it into R2M. And then this can be a totally real subspace of C2M. And by the property I discussed, this will be polynomially convex embedding. So this is polynomially convex. So therefore, we can say that N is less than or equal than 2M. The other observation is that if I take any embedding into Cm, topological embedding, doesn't have to be smooth, then it is a theorem by Browder and Duchamp and Stout that this is not polynomially convex. No closed topological manifold of dimension M, which is half of the real dimension of Cm, can be polynomially convex.
So I think you said this, but M is a real manifold of real dimension M.
Yes.
Okay.
Yes, this is a real manifold of real dimension M, and it's closed. And so we naturally get a bound between M and 2M. Could be cool, yes.
No.
Yeah, so for concrete examples, let's just take M1. So this is just the circle. Then we know that a circle cannot be polynomially convex in C. So C is not good, but you can find a polynomial convex embedding of S1 into C2. So this is the case which is most well known, most studied, that if you have a curve, this is what Eric was mentioning, that if you have a rectifiable curve in Cn for n bigger than 1, then there is a dichotomy. Either S1 or the curve is polynomially convex, or its hull is a one-dimensional complex variety that S1 bounds. But a generic S1 in C2 will be polynomially convex.
So saying it bounds an analytic variety, that's the same as saying it's the boundary of a disk?
No.
There is something different.
It could be something singular.
So in the context of this problem, we look at smooth embeddings of S1, but in general, you can have, this dichotomy about the convexity holds for rectifiable curves, for example.
No, but the variety that it bounds is what he's asking about.
Oh, the variety might be singular.
Might be singular, could have higher genus.
Yes. Yeah, it's not necessarily a disk. Okay, and then, so this is n equal 1, and the special case n equal 2. So now we have a surface. So then C2 is no good by the previous statement, so this cannot be polynomially convex. And then M2 sitting inside C3, well, this is already a non-trivial problem. I mean, the answer is known to this. I will mention it in the context of the general statement, but already this question is not trivial. And I'd like to give one motivation why this question of why the embedding problem may be interesting, and it's the following observation, that suppose I have this map phi into Cn, which is polynomially convex. Then by Ockervale, Vey. Okay, by even better. By Ockervale, holomorphic functions in a neighborhood of M can be approximated by polynomials. And this will be the embedding, so this will have no interior in Cn. So we may assume that this is also the space of all continuous functions on. Okay, so this is not automatic, but it holds in many cases. Then what we can say that, well, if we write phi as in components, M, then each component is a map from M into C. It's a smooth complex valued function. And from this, we can say that any continuous function on M is a uniform limit of polynomial combinations of the set of these functions, which is the same for all functions. So that sort of gives you an approximation on your manifold M by a fixed collection of smooth functions and their polynomial combinations. And so you get some sort of a polynomial approximation on a manifold where polynomials are not even defined or make sense. And so this we can call generators of the space of complex valued continuous functions. And we're looking for smooth generators in this case. Okay. All right, so now let me discuss what is known about this embedding problem. And I'm going to start with the case of a homeomorphism rather than smooth embedding. In this case, we know everything, actually. And this is the result of Vodavoz and Zeidenberg. And their method is completely non-geometric, so they start with X, which is a simplicial polytope. So it's a topological space that has the structure of the simplicial polytope, and they look at the space of continuous functions on X, and they say that this contains n+1 generators. In the sense that every continuous function is a limit of polynomial combinations of the generators.
Is n the dimension of the polytope?
Yes, sorry, I forgot to mention. Of dimension n. And so if we call these generators phi1 to phi n+1 and construct a map phi, then we get a map from X into Cn+1. And from the fact that these are generators, you can conclude from this that this is a homeomorphism, and the image is polynomially convex. So in particular, this holds on any manifold that has a triangulation. So in particular, it holds on every smooth closed manifold. So that applies to our setting. The sort of negative side, this is a very strong result, but the negative side is that it's only a homeomorphism. And the way they construct, so the methods that they use, this is the method of uniform algebras. There is a uniform algebra approach to polynomial convexity, and that's what they use here. And this embedding comes only as a sort of as a corollary. The problem with this is that because it's such a non-geometric construction, we know very little about this embedding. We don't know anything about sort of singularities of this map. You know, it's very, very non-singular. It's not possible to have smooth generators. And in terms of approximation theorem, you sort of approximating continuous function on x by continuous functions, and that may not be as desirable. Okay, so that's sort of one important result. And the second result, to formulate the second result, I'm going to quickly discuss totally real manifolds. So you take a manifold M, real manifold in Cn. You take a point, you look at the tangent space TPM. It's a real subspace of Cn, or tangent space to Cn. And we say that M is totally real at P if the space, it's a linear subspace of Cn, and we say that has no non-trivial complex subspaces. So from this, it's clear that totally real may have at most dimension and real dimension, so half of this dimension, in which case it is called maximally totally real. And I'm going to need in the future that if TPM has a complex subspace of maximal dimension k, then I would say that CR dimension of M at point P is k. So in general, if you have a lower dimensional manifold, then this dimension may jump when you go from point to point. And then you sort of going to call these CR singularities. But if this dimension is constant, then M will be a CR manifold. But in our case, we're going to be interested in totally real. So these are CR manifolds of CR dimension 0 everywhere. And totally real means totally real at every point. So as a primary example, this Rm, for example, would be a maximally totally real submanifold of Cn. Okay. So the next result, which is a sort of the most important result probably in this direction, is due to several people, Forstnerich, Rosé, let me put this way, Lofwald. They proved the following, that if M is already in Cn, or capital N, is a closed, totally real manifold, then there exists a C2 small perturbation of M, which is polynomially convex. So a C2 smooth small perturbation of a totally real manifold is going to remain to be totally real because this is a stable condition. If this subspace doesn't contain any complex subspaces, then you can wiggle it a little bit and it's still going to be totally real. And that gives a way to construct polynomially convex embeddings.
Not just existence, but for sort of a generic.
So this is a result for any M which is already embedded in Cn as a totally real manifold. Then going from totally real to polynomial convexity is just a matter of finding a small perturbation, and it will be polynomially convex.
I was sort of trying to get a picture in my mind of among the small perturbations, which ones will be convex? Is it like both?
It will be a dense open subset. And so that raises the question, which M admit a totally real embedding? Into Cn. Those ones that we can embed, we can then further perturb, and we're going to have our polynomially convex embedding. Well, this question has complete answer. And one way to do that is to look at some embedding of M into Cn, and then look at the Gauss map. So you look at the space of, so this is a Gauss map, and it goes into the Grassmannian of real M planes in Cn. So this would be 2 capital M as a real manifold, and this is the Gauss map. And then to say that you have a totally real embedding, that means that the image of this Gauss map and this Grassmannian, at every point here you have a point which corresponds to a M plane in R2n, and you don't want this plane to contain any complex positive dimensional subspace. And these are computable objects. These are for every such dimension you would have a manifold, and you can avoid them. And this is a just transversality theorem. And so by doing this, you can have in transversality. Okay, there are 2 ways to do that. You can either use a parametric transversality theorem, or you can do that in jets instead of looking at the Gauss map, in which case you can use Thom's transversality theorem, but it gives the same result. And the result is that if n is bigger than 3m over 2 minus 1, then M of dimension n admits a totally real embedding into Cn. Okay, so this transversality theorem, it not only gives you the statement of transversality, in which case you can say that if M is sufficiently small dimension, then you can avoid all the bad points in the Grassmannian. But it also gives you a way to compute the dimensions that work, and that gives you this estimate. Okay. So I want to mention that this is a sort of general result. This works for any closed manifold of dimension M. If you look at a specific class of manifolds or particular manifold in mind, then
So and there's something wrong in the case when happening that is 1 and if n is 1, it doesn't seem to be the right answer. But you can get that a circle. If you bet a circle in C, then it's not polynomial convex.
yeah, this is totally real.
Right.
So S1 in C is totally real because
Yes,
you just don't know. Yes.
But
Oh, it doesn't
have
work?
Perturbations, which any perturbation that was done is not.
No. So if M is equal to 1, you have 3 halves minus 1, so it's a half.
Yeah.
So 1 will work.
Yeah.
So S1 can be embedded as a totally real manifold in C. Oh, here. Okay, here.
That theorem.
So here I can say
N must have.
M has to be bigger than 1. Yes.
That's the thing. Isn't it?
Yeah.
Thanks.
Thank you. So I just want to, so this is general sort of inequality that works for all m-dimensional manifolds, but if you look at specific ones, let's say if you look at a sphere, Sk, then this naturally sits inside Rk plus 1, and you can embed it into, therefore, Ck plus 1. And so that's totally real, and in fact, polynomially convex. And then, so which is much better, of course, than what that general theorem gives you. But, and then you may wonder, can Sk be embedded into Ck as totally real submanifold? Well, there is a general result by Wells, which says that the Euler number of Sk has to be 0. Sorry. So let's say if so, then Euler number of Sk has to be 0. That's true for any closed manifold. If it admits a totally real embedding into Ck of the same dimension, same complex dimension, then its Euler number has to be 0. So that eliminates all spheres of even dimension. So you only have possibility for spheres of odd dimension, and it's a result by Gromov that for odd dimension only S1 embeds as a totally real in C trivially, and then S3 embeds into C3. And all other spheres do not admit totally real embeddings into corresponding Ck.
So it's somehow the crucial. It's more than the tangent bundle being trivial. That's
Yeah. So yes. So for totally real immersion, the if and only if condition is that the complexified tangent bundle is trivial. And in this case, for any sphere, it will be trivial. But that only gives you an immersion. So Weinstein has immersions into into R sort of, I'm going to write it like this, RCK, and it's a Lagrangian immersion with a standard symplectic structure on CK. And these Lagrangian immersions are in particular totally real. So for every sphere, we have a totally real immersion into CK, but only S1 and S3 admit totally real embedding.
What's the key property of S3 that makes it possible?
I don't know how to say this, but this is the application of Gromov's H principle. I don't know why it works in this dimensional setting and then doesn't work in high dimensional settings.
So my guess was that maybe the triviality of the tangent bundle would be a crucial.
Oh, the tangent bundle, I see.
Tangent bundle, real tangent bundle being trivial, but that's also true for S7. That's the other one where.
Yeah, but this is a sort of. Okay, and another thing that I probably want to mention here is that this, let me call it formula star, that this formula star is sharp in a sense that for any m and n that do not satisfy this inequality, you can find an m-dimensional manifold that does not admit a totally real embedding into this Cn. Okay. And these are explicitly constructed, these examples explicitly constructed by Ho, Jakobowicz, and Landweber. Okay. So what this example shows that if we want to improve this inequality, this inequality now works for totally real embedding, therefore it works for polynomially convex embeddings. But if we want to, but polynomially convex embedding does not have to be totally real embedding. We do not require the embedding to be totally real. And so if we want to improve this inequality, we necessarily must admit CR singularities. We must admit sets on the manifold in the embedding where the tangent space will contain complex directions. These are what I will call these CR singularities. And so I'd like to mention two results. Which both due to Purvi Gupta and myself. And we have modest improvements to this inequality. So again, we're working with a smooth, closed manifolds, and then we say that 2K manifold can be embedded into C3K minus 1 for K bigger than 1 as a totally real, as a polynomially convex manifold. And the idea is that you embed with these isolated CR singularities, and then you sort of modify this idea of for Sneridge-Rosé low world, and you do the perturbation so that it still gives you polynomially convex embedding. And the second result is for a different dimensional setting. And here we have odd dimensional manifolds, 2k plus 1. K is bigger than or equal than 2. So this also admits a polynomially convex embedding into C3K. So in this case, the set of CR singularities are closed curves. So from the transversality theorem, what we get is that CR singular sets are closed manifolds. In this specific dimensional setting, we expect one-dimensional singular sets. And the idea of the proof is very different. So we couldn't really do the perturbation of this sort to get polynomial convexity. But instead, what we did, just sort of schematically draw a picture. So let's say that this is my manifold M, and inside, somehow, I have these CR singular points, which form a circle. The circle itself may be non-polynomially convex, we don't know. But the idea of the proof is to come up with a model. So you have sort of a this is explicitly written model. So this is, let's say, M mod, and then this is N mod. So this is a totally real manifold with a set one-dimensional circle of CR singularities. And so this is CR singular, the rest is totally real. This is CR singular, the rest is totally real. And the idea is sort of to cut out a neighborhood here. Remove it from the manifold, and then glue in the model. But you want to glue it in a way so that this picture is completely misleading because for dimensional reasons. But sort of the idea is that you would glue it like this. And the model has the property that this circle of CR singular points has a neighborhood which is polynomially convex in a manifold. And if you have that in your original manifold, then you can do the perturbation so to make the whole thing polynomially convex. But the most difficult part is to show that you can actually embed, so you can actually replace this neighborhood by a model. In fact, we have two models because, as it turns out, that there is a topological abstraction to this totally real. We call this cylindrical totally real cobordism, and there is an abstraction which lies in the Stiefel manifold that may prevent you from gluing through totally real embedding. But once you have this for sort of, once you have two models, then you can say that one of them is going to work. And this, again, this is a relative version of Gromov's H principle here for totally real sort of embeddings. And in the last sort of minute, I just want to summarize what, sort of give the global picture, what we have now. So we looked at M2, and we said that this cannot be polynomially convex in C2, but this works in C3, and this is the optimal result. You cannot do better than this. And then M3 you can embed into C4, and this is through totally real embedding. So this is also through totally real. And then if you take 4-dimensional manifold, then you can embed it into C5. And this is theorem 1. And then if you take M5, you can embed it into C6. And this is our theorem 2. That's also optimal. But the next case, if you take something 6-dimensional, then we know that this could be embedded into C8 from the results that I presented. But this is already may not be the optimal result. So if we believe that this dimension should be n+1, then perhaps this should be S7. But the best we can do at the moment is S8. And things are even worse if you increase the dimension of M. Thank you.
Questions?
So in the case of curves, there was this nice dichotomy between, if you had, of course, automatically totally real embedding, it's either going to be polynomial convex or it bounds
A variety. Yeah. Yes.
Is there anything that's in that direction for totally real embeddings of higher dimensional manifolds?
No. So in the context of our theorem, the additional result that we have, that not only we have polynomially convex embeddings, we can also have an embedding of M4 over M5, or in all the settings here, dimensional, which is not polynomially convex, but the hull does not contain any analytic structure, so there is no disk inside. So I don't think this is true as soon as you sort of assume bigger dimension for your compact, more than one.
And so there's no real feeling for what is going wrong, and there's no general pattern that can be seen about what's going wrong in these kind of non-generic cases where this theorem of
there is a hull and no analytic structure.
well, you have this genericity statement that most C2 perturbations of a totally real submanifold
Yes.
would actually be polynomial convex. But
Yes, but that's for totally real.
yeah, so I was just asking
Yeah.
about the totally real case. So
The non-generic cases, yeah, so yeah, for non-generic cases you may have a hull, but it's the structure of that hull is completely mysterious.
Well, I had two questions, but
Yeah.
hopefully they're not too far off from what you were speaking about. So in the embedding problem, you were talking about finding the best n, which would work for every n-dimensional manifold.
Yes.
But might there be like some n-dimensional manifolds that do better than that worst n? Like there's a group that works for 17, but some of them work for 16 and some work for 15. Can that happen? Is that
Yes,
true?
yes. So I gave example of spheres.
You did, okay.
So sphere, this sort of direct inclusion gives you a much better already.
Okay.
Yeah, and then there is a class of orientable manifolds. This works for orientable or not. It doesn't matter. I mean, but if you have orientable, they usually can be embedded as a totally real or nicely embedded into smaller dimensional manifolds. And then I think for orientable ones, you may have a better bound rather than
Okay, so even after you solve this problem, you still have the problem of then characterizing which ones go into which dimensions.
True, if one wants to do that, yes.
Thank you.
I was also wondering about this list. Is there any counterexample to MK embeds in CK plus 1?
No. At some point, I thought that maybe it's always just one dimension more, and we're just not able to prove it. But recently we were looking at these CR singularities. There's sort of what prevents us from going further is that these CR singularities, you need to understand the topology of them. And there are certain situations, generic situations, when there are these really bad points on the CR singular set that may actually have local hull. But we don't know. It's sort of, so now I'm not so sure anymore if this is the optimal dimension. The 1 plus 1 is the optimal dimension. Sorry, the n plus 1.
But
So-
there's no.
But there's no counterexample.
But if you could do that, this local hull, that would give.
That would be a counterexample, yes.